going. Yeah, it must be. Oh, great. Hey there, Lee. All right. Let's review, folks. What is a function? Now, a function is a lot of things, but there's a main concept we're looking for here about what a function is and what you can do with a function. It's an input-output machine. It's a shame they don't call them input-output machines, but instead they call it a function. So we have ourselves a function, such as anything. I'll just write x squared minus 5. And then whatever you put in, this whole thing computes to be what you get out. And as we said, input, output, it's a table of values, it's a coordinate on a graph. But most importantly, it's an input-output machine. And so what does it mean to compose two functions? Well, let's say that we start with a single input, x, and we input it into one function, and it outputs into some other value. So there's your output. This is just a way sometimes textbooks map or draw a picture of a function. The whole idea is that you're at a particular number, and when you run it through the function, you come out at a different particular number. And then you take that output, and it becomes the input of a new function, let's call it g, and then you have a new and final output. So you run a product through one machine, and then it gets run through another machine. And to compose two functions means to come up with one single function that will take you from the original input all the way to the final output. And what do we call that new function? You could call it another letter like h. You could call that the h function. But instead of calling it h, we call it f circle g. F circle g means the same result of putting in an input and getting in an output that you would get if you did the input through f first and then g. So that's what f circle g means. It's a function that gets the same result as going through two separate functions. So that's a composition function. More importantly, the notation we learned said that f circle g of an input x is the same as f, and what do you plug into f? G of x. So you're actually plugging a function into a function. So Gabe asked, what do you call this, like mixing two functions together? It's called composing two functions, but it really just means that you're inputting a function into another function. So that's like function inception. I like to mention that movie because I don't know why. I just thought it was a fun movie. And I like the idea of dreaming within a dream. I've never done that. Okay. Then what then? What is an inverse operation? So this is separate. I'm not asking what's an inverse function. I'm saying what's an inverse operation. What are the inverse operations? We listed 3 pairs.
Subtraction, addition, multiplication.
Yeah, so our inverse operations are plus, minus, multiply, divide, square, square root, or generally speaking, it could be cube root, or really any x to the n, nth root. So it's really a power and a root. That's what opposite functions are, a power and a root. So those are inverse operations, and what do they do to each other? Yeah, they cancel each other out. So if you did one followed by the other, it would always cancel itself out. Like for plus minus, if I had 10 plus 5 minus 5, it's just 10. And if I had 10 and I multiplied by 2 and then divided by 2, it's just 10. And then if I did 10 squared, square rooted, it's just 10. Right? So inverse operations have the power to cancel each other out, and that is at the heart of algebra. Because when we write something like 3x squared minus 7 equals 5, well, we want to get x by itself. And I don't know if I showed you this. This is really fun. Did I show you this? Here's x, right? And x is wearing clothes. X is wearing a squared pants, a ×3 shirt, and a -7 belt. So watch. I'm going to undress x. Actually, this analogy is sounding a little weird. I'm going to undress x. So watch how I do it, okay? Normally, did I do this? Okay, I did. So normally what you would do is you just do everything and simplify as you go. But watch. So if you simplify as you go, this is what you're used to seeing. You add the 7 over, then you have 3x squared equals 12. And then you divide the 3 off, and you simplify as you go, and you get x squared equals 4. Then you square root, you simplify as you go, and you get x equals 2. Well, watch how fun it is if you undress the x and dress up the 5. Okay? I'm going somewhere here. So I'm going to add the 7 over to the other side, and I'm going to leave it as 5 plus 7. Then I'll divide up the 3, and I'll leave it there. So now it's x squared equals 5 plus 7 over 3. And then I'll square root both sides, and I'll leave it there, and x is equal to the square root of 5 plus 7 over 3. So there, I took all the clothes that were on X, and I moved them over, and I put the clothes on 5. Isn't that kind of fun? I mean, that's interesting. And I did all that through opposite operations. So I canceled the clothes off of X, and they reappeared over on the 5. See, it's just so unfair. It's a good analogy, but it sounds inappropriate. I'm not being inappropriate, but it sounds right. Maybe if I just focused on like socks or something.
Like it's your kid.
Yeah, someone you're allowed to undress in an appropriate way. Yeah, I guess so. Oh, it's just too bad there's not a better analogy. Does anyone have a better analogy for this?
Yeah, I don't really like it on there. Just like giving your clothes to somebody that's more needy or like that's in need.
Yeah, or maybe taking off a costume. Maybe you're just a costume. You can talk about layers of an onion, but you don't take layers off an onion and put it on a tomato, right? Yeah, it's weird. Okay, well, if anybody has a better analogy, that'd be nice to see. So, opposite operations, they're at the heart of algebra. So what does it mean to find the inverse of a function? So this is a very different use of the word inverse. These were inverse operations that cancel each other out. What's an inverse function?
Function that reverses the role of input output.
Exactly right. It reverses the role of input-output. That's probably the best definition. Just like a function is an input-output machine, an inverse function reverses the role of input and output. So if I had some function f, and I had a table of values that was going, say, 1, 2, 3, and it turned into 5, 10, 15, then my inverse function, f inverse, would take input values. It would take the input values 5, 10, 15, and create the output values 1, 2, 3. Okay? So it's just like, I want you to watch the order of operations here, okay? Here I'm saying, if I plug in a 3, what will it equal? 15. Here I'm saying, if it equals 15, what must I have plugged in? 3. So it's turning the question around on its head. So that's inverse operations. It reverses the role of input and output. Now, how do you know that two functions are actually inverses? And I say list 3 ways, but we actually know 4 ways. So what are the 4 ways we know that two functions are actually inverses? That's if a function is invertible.
Oh, okay.
A function is invertible if it passes the 1-to-1 horizontal line test. A function is invertible if it's 1-to-1. It's 1-to-1 if it passes the horizontal line test. Okay, so how do we know that two functions are actually inverses? Well, here's one way. If you look at their infinitely long table of values, and how do we know that two functions are inverses?
If you graph it.
Very good. If you graph, let's say you take one graph, which is a parabola, and then you have, okay, so that's f of x equals x squared, but I'm only looking to the right of the y-axis. And the inverse of x squared is square root of x. So that's one way in which inverse operations really are inverses. So the inverse function would be the square root of x, which looks like this. So f of x equals the square root of x. And the whole idea is that if you look at inverse functions, they will be mirror images across the diagonal line y equals x. And keep in mind the diagonal line y equals x, that's the equation of a straight line, y equals 1 over 1, x plus 0. So that is y equals mx plus b, but we just say y equals x, and that means the diagonal. So you know you have inverse functions if they are mirror images across the diagonal line. It's really helpful to tilt your head and actually look head on and see, you know, that they really are reflections across that dotted line. Okay, that's 2 ways. The tables are swapped, and they're mirror images of each other. What's another way of knowing that two functions are inverses?
Is there a name for the steps, the 4 steps that we did, or is that?
Those are, well, thank you, that is the way. And it's just the 4 steps that we follow to find an inverse. If you properly follow the steps for finding an inverse, then it will in fact be an inverse. So take a look at, say, this one. I'm going to use my example that I just wrote here. 3x squared minus 7 equals 5. Oh, that's not. How about I make it 3x squared minus 12? So I have 3x squared minus 12. Now, Omar, this is, it's for everybody, but it's especially for you because you were here. So step 0, you write down the function. What's the first thing you do? Right, yeah, we write down the problem, then what do we do?
Replace f(x) with y.
Yeah, replace f of x with y. And this is just a notational difference, okay? F of x and y are synonymous. They both are referring to the output of the function. But f of x clearly is written like a function, whereas y is written like a coordinate xy. Okay, so f of x implies output, whereas y and x imply coordinate. So we have the coordinate. What's step 2? Yeah, we switch x and y. Now, at a deep, deep level of meaning, what did we just do? By switching the x and the y, we inversed it. We swapped the role of input and output. Okay, so that was step 2. We switched the x and the y, and then step 3, solve for y. Yeah, now we just go about doing algebra. So again, I'm going to undress the y. No, I'm kidding. I'm never going to keep saying that. Y is being squared times 3 minus 12. So I'm going to add 12 to both sides. And so I have x plus 12 equals 3y squared. And then I divide off the 3. And then I have y squared equals x plus 12 over 3. And then I'm going to square root both sides. And we end up with y equals the big square root of x plus 12 over 3.
You can call it remove your gear.
Oh yeah, maybe gear. There we go, gear. That's closer. That's closer to something I can say publicly. I like that. Okay, and then finally, what's the last thing we do?
Replace y.
Yeah, we replace y with f inverse. F to the negative 1 of x equals x plus 12 over 2. Okay, so if you follow those 4 steps, now I know that that and that, those are inverses. So we've covered 3 ways to know so far that 2 functions are inverses. 1, you look at their infinitely long table of values and all the values are swapped. 2, you look at a graph and the reflections across the diagonal line y equals x. 3, you follow the steps. What's the last way of knowing that 2 functions are inverses? What?
You graph them to see if they're mirror.
We'll graph them to see if they're mirror images. That counts as that one.
Then like the one-to-one.
The one-to-one, if the horizontal line test tells you if a function is one-to-one, and if it's one-to-one, it's invertible. So you can only actually find an inverse if the function passes the horizontal line test. Okay, so what was the 4th way? It would probably look the most complicated, but it had to do with function compositions, which is one reason we learned them.
Oh.
Two functions are inverses if f of f inverse of x is simply equal to x, and if f inverse of f of x is equal to x. This is really unique. It means whatever you input, that is the output. So like if I plug in a 5, I get out 5. If I plug in 10, I get out 10. If I plug in 20, I get out 20. Like this is the most useless function in the world, right? It's called the identity function because what you plug in is what you get out. But that'd be funnier if we called it the useless function.
It's called identity.
Identity. Yeah. Okay, so let's just see if it works. I'm going to write down the function or the structure of f. So that's 3 something squared minus 12. And then I will input the inverse function, which is root x plus 12 over 3. So let's see. Does everything cancel out? It should. The square and the square root cancel out. The 3 over 3 cancel out. And the x plus 12 minus 12 cancel out. And the whole thing is equal to x. The closed canceled each other out. I get nothing. Okay, now I'm going to write down the structure of f inverse. So it's root something plus 12 all over 3. And if I input the function f of x, that'd be 3x squared minus 12. Well, again, 12s cancel out. 3 over 3 cancels out. And the square root of x squared cancels out. And sure enough, it equals x. So in both cases, the composition of the functions end up just equaling x. And that's the technical definition of an inverse. You read, textbooks on mathematics, that's the definition of inverse. That's just a property. That's just a property. This is a procedure. But this is the definition of inverse. Okay, there we go, folks. So we did a lot with inverses. Now, let's see where we got. Today is March 25th. There is no section 5.3. We're just going to move on and finish all of chapter 5 today. And then Wednesday, we'll start chapter 6. And all of next week, we can do chapter 6. And then you'll have your test. Just today on Canvas, under announcements, there's an announcement where I post all of your documents. So I have the notes for chapter 5, chapter 6, the log practice we're going to do, as well as the practice test for chapter 5, 6, as well as the solutions to the practice test for 5, 6. So like, for instance, one thing you could do tonight is just go straight home and download the practice test and the practice test solutions and go ahead and start reading the solutions as far as you can handle. You know, just go ahead and start looking at the problems, being like, oh yeah, okay, we did that. Oh yeah, okay, we did that. Oh yeah, okay. Well, we haven't done that yet. Or go ahead and read now what you've already covered. That way you'll start feeling confident about the test. You can never study too much. Okay, why? Oh, I have a joke. Why did the bird cross the kitchen? Tweet, tweet, tweet. Tweet. I tell my daughter that joke, she's 2.5, and I'll ask her now, why did the bird cross the kitchen? And she'll say, tweet, tweet. And then just the other day, I brought her a snack when I picked her up from school. Wait, what?
It's like, tweet, tweet.
Yeah, I brought her a snack when I picked her up from school, and I said, honey, do you know why I bring you a snack when I pick you up from school? And she answered it correctly the first time. She said, because you love me. And I said, yeah, that's true, because I love you. And the next day I asked her the same thing. I said, honey, do you know why I brought you a snack? She said, tweet, tweet. I couldn't believe it. I mean, that was very clever of her to say. All right, so how far did we get, folks? We started doing these, and we did 1, 2, and 3.
Oh yeah,
We finished.
Oh no, we just did 1 and 2?
yeah.
Yeah, 1 and 2.
I mean, we did all of them, the first part of it, as far as.
Right, the first part, we said that all of them are 1-to-1.
Yeah.
Okay, so let's go ahead and start with number 3 then. And everyone will benefit from getting to see these steps. We won't necessarily do all of these problems, but we'll do quite a few of them. And so number 3, we'd like to know the inverse of that function. So we're going to start, you write down the problem. So I'm going to label my steps here, okay? Step 0. Again, the first thing you do is just write down the problem. F of x is the square root of 3x minus 1 plus 5. And then step 0, we replace the f of x with a y. 3x minus 1 plus 5. And then we switch the x and the y. Now, to be fair, I can really imagine how someone might want to just skip step 1 and 2 and be like, come on. I know that f of x is y, so I'm just going to go ahead and write down x equals square root of 3y minus 1. Does anyone feel tempted to just do that? I mean, it's okay, you can all be honest. Yes, you all feel tempted to do that. But this is our process, right? We're saying, okay, we have a function. It's an input-output machine. I'm going to rewrite it as a coordinate machine, x, y. Every coordinate that I can plug in here to make a true sentence is a coordinate on my graph. And then I'm going to switch the x and y and say, I'm going to switch the role of input and output. And now we go about solving algebraically. So algebra, we've got the letter y here, and it is geared up. Right? It's wearing all this gear. It's being multiplied by 3, subtracted by 1, square root of plus 5. So if it benefits you, I would write down the story of y. Because this is what I do in my head. Writing it down doesn't hurt. So what happens to y? It gets multiplied by 3, it gets subtracted by 1, it gets square rooted, then it gets added by 5. That's the forward story of y. That is what is happening to y. And so to solve algebra, you go backwards and reverse. So again, you can write it down. You're going to subtract 5, you're going to square, you're going to add 1. Whole process for you. You know exactly what you're going to do as you do it. And believe it or not, this is what you have been doing your whole life, ever since grade school. Every time you've ever done algebra, you've told the story of y or x, and then you went backwards, peeling off the layers of the onion as you play. Okay, so let's do it. I'm going to subtract 5 from both sides. So now I have x minus 5 equals root 3y minus 1. Done with that step. Then I square both sides. Isn't that nice? You can just look at it. You just see it there. So now I have x minus 5 squared equals 3y minus 1. Done with that step. I'm going to add 1 to both sides. So now I have x minus 5 squared equals 1 equals 3y. Done with that step. And then I divide both sides by 3. And so that's y equals x minus 5 squared plus 1 over 3. That's the completion of the algebra process. And then the very last step, step 4, was to just write it as an inverse. So we write f inverse of x equals x minus 5 squared plus we just did the 4-step process. We just did a whole bunch of algebra. The question on our mind, whenever you're done doing algebra, should be,
What's it look like?
well, yeah, what's it look like? And also, are we right? Like, is that really the answer? Because maybe we made a lot of mistakes. You know, we could have done some computational mistakes, made some mistakes with negatives, who knows? We could have made a lot of mistakes. So how can we check fast if it's a function? We could do a table of values, but unless you make your table of values infinitely long, you don't really know. You could, well, we did the 4-step procedure.
But that one.
You can compose and see if it works out. And that's the definition. That would be the best bet. Or quick and dirty, you can just graph it. Right? If you just graph it and you see that it's a mirror image, then that gives you a lot of confidence. Is it a proof? No, because maybe you have to zoom out pretty far to see the first time the symmetry breaks down and they're not mirror images. But, you know, theoretically, just graphing the two would be a pretty good, quick way to do it. So I'm going to graph square root of 3x minus 1 plus 5. There's 1. And then the answer we got was x, I can't really see it.
X minus 5 squared.
Minus 5 squared, what?
Plus 1.
Plus 1 divided by 3. Okay, so root 3x minus 1 plus 5. And yeah, the parabola x minus 5 squared plus 1. Okay, so now take a look here. And I'm going to put in my diagonal line. Which part of this, so keep in mind that the red graph was just a single half of a parabola tilted sideways. So which part of this blue parabola is our inverse?
The right side of 5.
Yeah, the right side. Now everybody, I'm going to try to cover up part of it. Can you all see? If I cover that up, okay. This blue and that red are inverses.
Yes.
Okay, are they mirror images? Cock your head and look. Yeah, these are definitely inverses. So not this left-hand portion of the parabola, just the right-hand portion of the parabola. Now how would we know that if we didn't graph it? Because what we're saying is that the inverse is strictly the right-hand side of this parabola from where to the right?
5. So we need to do 5.
So we'd have to narrow that down, and we'd have to say strictly x is greater than or equal to 5. Now how do we know that? Why did we know that it had to be greater than or equal to 5? Well, yeah, anything less than it would be not passing the one-to-one horizontal line test. But also notice we're switching the role of inputs and outputs. So keep in mind here that the outputs for the red function start at 5 and get bigger. So if the outputs of the original function start at 5 and get bigger, the inputs of the inverse start at 5 and get bigger. So the range, the output of the first function tells you the domain of the second function. But again, you can always graph it to see that. Okay. Well, there we go. That's a nice sample problem there. Let's try another one. Now, for the sake of time, I would really like to I don't feel the need to focus on these cube root ones, or at least not a bunch of them. So how about everybody cross out number 5, and we're just going to do number 4. Yeah, I like that. We're going to do number 4, but we're not going to do number 5. All right, so here's number 4.
5 was a good one.
5 was a good one?
Yeah.
I just
Oh.
crossed it out.
Well, I mean, if we have time, we can always go back and do it. Yeah.
Absolutely. Sorry.
All right, so we're going to start by writing f of x equals 5th root of 3x minus 1, which you say y equals the 5th root of 3x minus 1, and then you switch x and the y, and now we're ready to do algebra. And again, you might feel like those first couple of steps were kind of pointless, but that is the structural notation. So what do we have then? Y is being multiplied by 3, subtracted by 1, and 5th rooted. So if you wanted again to tell a story, you'd say y is being multiplied by 3, subtracted by 1, and then 5th rooted. That's the story it's going. So what's the backwards of that? Squared, not squared, or to the 5th. To the 5th, add 1, divide by 3. So we'll take both sides and raise it to the fifth power. That cancels out that fifth root, so now we just have x to the fifth equals 3y minus 1. Done with that step, so then we add 1 to both sides. So we have x to the fifth plus 1 equals 3y. Done with that step. Right. So that gives us y equals all that. So y equals x to the fifth plus 1, 3, which we really write down as f inverse of x to the fifth plus 1. Now, the whole writing down the story thing, you don't have to do that. If you feel more comfortable just doing the algebra, that's fine. I saw a student earlier today do something that I'll share with you, though I don't actually want any of you to do it. But I thought it was interesting. So the student had this problem, and they went ahead and they wrote y equals, which already. And they said to themselves, okay, I'm going to start moving these symbols over. So the fifth root became x to the fifth, the minus 1 became plus 1, and the times 3 became divided by 3. And they just wrote it down. And that's what I saw on their paper. And when I saw it, I started weeping. Like just crying, tears. Of, oh no, you know, there's no work. You just skipped right to it. But at the same time, did you follow what I did? And did it kind of make sense? I mean, it's possible. I mean, sure, yeah, you could do it if you see it well enough. But that's the thing, it takes a lot of training to train your brain to see all that happen so quickly that I don't recommend it at all. I think you should go ahead and do the steps and do the algebra. Yeah, you have to show me the steps anyway. There's just too much opportunity for a mistake if you do it that way. Way too much opportunity for a mistake. Okay. All right. So how do we check that that's actually the right answer? Yeah, might as well graph it. That's the fastest way. So I'm going to do the fifth root. The fifth root of 3x minus 1. To do a fifth root, you raise it to the power of 1/5. And then I will do what we just did, which was x to the fifth plus 1 divided by 3. So now take a look at how fun this is. Again, cock your head to the right and look at it. Isn't that fun? It's obviously symmetric. It has a really pleasing visual property to the eye. And you know now that they're inverses. Furthermore, do they both pass the horizontal line test? Yeah. Does that pass the horizontal line test? Does that pass the horizontal line test? Now, it might look like it doesn't pass the horizontal line test right here. But it's still going up, up, up very, very slowly, and then up, up, up very slowly. So no matter how much you zoom in, if you zoomed in a lot, it doesn't go exactly horizontal. It's still climbing. Very slowly, it's climbing. Okay. Questions about that one, folks? Leah, I'm sorry to disappoint you. I'm going to skip number 5. No worries. All right. Okay, so number 6. Notice number 6 has some interesting notation right there. What's it say? Four. Now, before we even start that problem, what would be a good idea? Yeah, let's look at it and know what we're talking about. So they gave us this function, and it says 3x plus 4 squared minus 5. And so there's, oh, got to turn it on. There's the graph, but they're saying only look to the left of -4. Does everyone see why that x less than or equal to -4, why that means look to the left of -4? So that's the only graph we're looking at right there. And does that pass the horizontal line test? Yeah. Yeah. Okay, so we're only looking to the left of -4. So now go ahead, everybody, and do that problem. You can write it down as the story of x if you like. You can just do the algebra the normal way.
Lee, had you ever considered just solving that whole equation right there in one step by just writing down the answer? Never done that in my whole life.
No.
I mean, now that I see it, I'm like, well, sure, do it. But only if it's one variable.
Right.
You know, it only works if it's one variable.
Hey, very nice. Yeah, nice help.
Yeah, do you remember doing this in a previous class?
Fine, I like how you're numbering it all out. And hey, I see you're strictly vertical. How's that working for you? Okay.
Which one?
Oh, yeah, nice story too. Had you ever done that before?
Yeah.
What do you think of it?
Yeah, I would it's easier to kind of keep in mind that.
Yeah, that's true. You don't have to keep telling
Can
the
we
story over and
share
over.
straight down the center what's happening next?
You're gonna what?
I didn't mean it like that. I know you're like. After that.
I'll be there until that's it.
Okay, folks.
Yeah.
I'll show you one more option for how algebra works. And again, I'm not saying you should do it this way, but it is neat to see algebra done in lots of different ways because it reiterates how algebra works. So watch this. This I would almost allow. So you've got your y, I'm going to solve for it. Notice I put x over here. I'm going to move all these symbols from the left to the right, and I'll cross them out as I go. So am I going to want to see? So I get the story y is being added by 4 squared times 3 minus 5. I'm going to go ahead and add the 5 over to here and get rid of it there. And then I'll go ahead and divide by the 3, or yeah, divide both sides by 3, get rid of it here. And then I'll square root both sides and get rid of it here. And then subtract the 4 and get rid of it there. That's almost legit. A little more legit than what I did a second ago. Because you're still one step at a time doing things over. Again, it's kind of magical. You see the result, but it didn't show all the steps in a nice orderly way like algebra normally works. Okay, then it's F inverse. Did everyone get this equation? All right. So there's our inverse. Now, how can we check our work? Right, we could do
Or graph it.
the function composition and or we could graph it. In this case, let's do both. Let's do both. So I'm going to go ahead and graph. Well, I already have my graph to the left. And now we just came up with a square root of, what is that? X plus 5 divided by 3 minus 4. Okay, now when I first, there we go.
With the square.
The -4 should be out of the square root.
Oh,
there.
thank you. Yeah, that's better. Okay, so visually, it's a little unclear what's happening here. We were only interested in the left-hand side of the parabola. So if I draw in my diagonal line, the left-hand side of the parabola is symmetric with what? Is the left-hand side symmetric with the red? Because I just drew in the red function. What's the red function actually symmetric with? If you turn your head, it should be obvious because they both go through that point.
Left side.
Yeah, the red function is actually symmetric with the right side of the parabola. That's not what we wanted. We wanted the inverse of the left side of the parabola. But my inverse that I just came up with was the right side of the parabola. So what happened? We didn't get the inverse of the part we wanted. Yeah. But keep in mind, did we do a square root in the process of algebra? So technically, what's that? Technically, since we did that square root in the process of algebra, that's plus or minus. So the plus root is not what we wanted. Let's try the negative one. Is that the mirror image of the left-hand side of the parabola? Yeah. The left-hand side of the parabola and the red function now are mirror images across the diagonal. Again, you tilt your head and you look. So that tells us that what we really needed there was the negative square root. Now that's very subtle, right? That's very subtle.
So whenever you square it, do plus and minus?
Whenever you square root in the process of algebra, it is a plus or minus. And like at that point, you have those two options. The plus or minus means you're either finding the inverse of the left-hand side or the inverse of the right-hand side. And you have to choose the appropriate one. Probably the fastest way to choose the appropriate one is to graph it. Lee, what do you think?
Yeah.
Okay.
I think it's good. You might want to double check this when you guys do it, because there are times where like you might slip that negative sign out of your mind.
Yeah. And of course, another thing you can do is do a table. A table with just one value. Try a table of values with even just one test coordinate. So in the original function, choose something easy by plugging in 0. 0 plus 4 is 4, 4 squared is 16, 16 times 3 is 48, minus 5 is 43. So now, what? Yeah, so now what happens if I input 43? If I had left the plus.
It probably would be two.
Yeah, 43 plus 5 is 48. 48 divided by 3 is 16. The square root of 16 is 4, and 4 minus 4 is 0. Oh, but gee, that worked. Oh, but you know what? The only reason that worked is because the square root of 0 is 0, whether it's plus or minus. So that was a bad test coordinate. So let's try, I'm going to try negative 2. So negative 2 plus 4 is 2. 2 squared is 4. 4 times 3 is 12. 12 minus 5 is 7. So now if I plug in a 7, 7 plus 5 is 12. 12 divided by 3 is 4. The square root of 4 is 2. And I need either plus or minus 2 minus 4 to equal a negative 2. And the only that.
Well, when it does it, it's positive 2.
Oh, but that's because I chose a test point on the coordinate to the right side of the parabola. I have to choose a point over on the left-hand side of the parabola. I'm going to choose the point negative 5. Oh my gosh. It's very subtle business, isn't it? So I need to choose a test coordinate that will actually be on my parabola to the left. So negative 5 plus 4 is negative 1. Squared is 1 times 3 plus negative 2. So now if I input a negative 2 here, negative 2 plus 5 is 3. 3 divided by 3 is 1. So it's plus or minus 1 minus 4. And which way will give me a negative 5?
Oh,
The negative 1 minus 4. So definitely it has to be negative. Okay, I did all that just to demonstrate that's how you could figure out which to choose plus or minus is by doing a test coordinate. Or you can just graph it. Very subtle. Okay, well let's, I think we're done with that one. And then we're going to do 8, 9, and 10. Okay, we're doing great. We'll do 7. Yeah, we'll finish this and then we'll take our break. So first of all, as always, the first thing we should do, graph it, know what we're talking about. So this is, 7, which is x squared minus 6x plus 5. However, I'm only looking to the left of 3. Okay, so what part of the problem am I interested in? Yeah, the left-hand side.
So when we're done, we better have a graph that's symmetric to this one, the left-hand side of the parabola. So let's do our steps.
And the function is x squared, so therefore y is x squared minus 6x plus 5. And therefore x is equal to y squared minus 6y. Oh, how interesting. You know what? I think I skipped this problem in the last class. Yeah, I'm pretty sure I did, because we have not reviewed completing the square. That's how I would do it.
Yeah.
The square, is that what you would do?
Yes.
Yeah, but we have not reviewed completing the square at all in this class. So I think that'd be a little unfair to just pull it out at the last minute here. I think that this would just be an example that we skip. Unless you want to see it. Okay, we'll see it. Great. What courage. So, first of all, y squared minus 6y. Everybody rewrite it as y squared minus 6y. Leave a little space and put the plus 5 again. I want to know if you can, this is a guessing game, if you can come up with a way to factor this expression, even though you don't know what's here, such that it's the same number twice. So I want y minus something times y minus something to equal y squared minus 6y plus something. It would be y minus 3. Now, how'd you guess that? Right, because we're always asking ourselves, what do you multiply to get this number that adds to make this number? And if I want to add the same number to equal 6, it would be 3 and 3. So now this is really y minus 3 times y minus 3. Now, if that really is what was there, then when you FOIL that out, it'd be y squared, and then minus 3y minus 3y, that's the minus 6y. And then negative 3 times negative 3 is positive 9. So that's actually the number that I wanted there. But if I put a plus 9 right there, that's just adding 9 out of nowhere. I have to subtract 9 out again so that I didn't actually change the value. So now what we have now here is that this thing became y minus 3 times y minus 3 squared. And this over here is just minus 4. So now what do we have? X equals y minus 3 squared. Well, it's not the answer. It's just now in a form that we can solve algebraically. Because now y is being subtracted by 3 squared minus 4. And now you can move the 4 over, move the square over, move the 3 over, and solve it.
It's basically making a function out of another function, so we can complete that function.
Right, exactly. Now, again, I'm not going to put this on the test because we didn't review completing the square when we were doing chapter 2. So we can just be done with number 7. Because at this point, you can totally do it, right? You can move the 4 over, and then you would square root both sides, and then you have the 3, and that would be your solution for y.
If they wanted to learn how to do that operation, would they be able to come see me? Would that be okay?
Oh yeah, of course. If you want to come practice completing the square, sure, it's a ton of fun. You can do that all weekend.
It's another toolbox or another tool for your toolbox.
Yeah, exactly. Okay. So that brings us to the last 3 functions. What do you notice about the last 3 functions? They're all rather pieces in the bottom. Yeah, they all have x in the bottom. What do we call those functions? Rational functions. Yeah, they're rational functions because they're fractions. We could call them fractional functions, but historically we call them rational functions. We already graphed them the other day, and we saw that they were all, since they were all rational functions, they all had vertical asymptotes and horizontal asymptotes. So there's the first one, for instance. And does it pass the horizontal line test? Yes, it does. Therefore, it is invertible. And what we're looking for is a function that would be symmetric across the diagonal line y equals x. So if we can just flip that function over the diagonal line, that would be our inverse. So let's go ahead and try it. Now, these next 3 problems, I want to emphasize something. These next 3 problems are really good algebra. Like, this is good, sophisticated algebra. And so my recommendation is that as you write down these steps, I would go home and do each of these problems 5 more times. Just do them 5 more times in a row,
So you feel very comfortable, very fluent, very like, okay, yeah, I can do these fast. Not that fast matters, but that you actually know what to do from one step to the next. And you'll memorize it
That's what
and know the process. What?
That's what I'm saying. I always say slow, smooth, smooth is fast.
Well, yeah, that's true.
And kind of that right there proves with this.
Yeah, it doesn't matter how fast you do it, but just that you know what to do next. So
Okay.
let's talk about that and ask the question as we go. So for number 8, our function is 3 over 4 minus x. And so that's y equals 3 over 4 minus x. And therefore, we switch the variables and we get x equals 3 over 4 minus y. So the question is, how do we solve for y? You know, this begs our highest capacity for algebra. We want to get y by itself. And currently, y is being subtracted from 4 in the denominator being divided into 3. So, and one more thing that you might want to do, what's the number in front of the y? It's a 1. So you could technically say y is being multiplied by -1, added by a 4, there's a plus in front of the 4, and then all of that is 3 is being divided by it. Okay, it's tough to tell the story of x, or the story of y in this case, because you're saying y is being multiplied by -1, added by 4, and then divided into 3. There's no opposite of being divided into. Well, yeah, I guess. So instead, what we're going to think about is, what's tricky about this problem? Where is y that makes this problem tricky? In the denominator. Don't we wish y was not in the denominator?
Being separate. If 3 over 4 into a fraction.
If it was 4 minus y over 3, you could separate it into 4 over 3 minus y over 3. That's what you mean?
Yeah.
But since it's 3 over 4 minus y, you cannot separate a denominator. If you did 3 over 4 minus 3 over y, that would be completely wrong. That way you can. You can separate a numerator, but not a denominator. Okay, so y is in the denominator. We're bummed about it. We want y not to be in the denominator anymore. So what can we do? How do we ever get rid of denominators? Multiply the reciprocal. You could multiply the entire reciprocal. There's only one part of it that you have to multiply by. If you just multiply by the denominator, it cancels the denominator. So watch, this is fun. I want to get y out of the denominator. I'm actually not going to get this y out of the denominator. I'm actually just going to cancel that y out of existence. But the y will show up over here, not in the denominator. So did I get the y out of the denominator? Well, technically, there's no longer a y in a denominator. I didn't get it out of the denominator. I canceled it. But it did show up on the other side of the numerator. Okay, so now we have, I'm going to rewrite this so the x is on the left. X times 4 minus 1y equals 3. And now you'll notice that we're no longer bogged down by this pesky denominator issue. Right? No more denominators. So first big trick, if you have a variable in the denominator, multiply by that denominator on both sides and it gets rid of the variable in that denominator. Okay, so now what? We want to solve for y. Y is being multiplied by -1, added by 4, multiplied by x. So we divide up the x. We start peeling the layers of the onion away from the y. So y is being multiplied by -1, added by 4, multiplied by x. So we divide both sides by x. That cancels. And then, again, y is being multiplied by -1 and adding by 4. So we would subtract 4. And then because it's -1y is equal to 3 over x minus 4. Now here I'd like to suggest one more fun move. We want to get rid of the -1 in front of the y. So your first impulse might be to divide off the -1. But dividing off the -1 looks a little clunky, right? If I divide off the -1, look how awful it looks. If I divide off the -1, I have this thing. Oh, what's that thing? It surely is y equals all that. Now, I could separate the numerator, as Emily just mentioned. That is 3 over x over -1, minus 4 over -1. And then what? You'd have to continue to process this 1 in the denominator of each time. Which you can do. It just looks clunky. So instead, we just want to get rid of the -1. What will cancel out a -1? Not a positive 1. You can multiply by a -1. Multiplying by a -1 is so much better than dividing by a -1. This is a nice trick. trick to know. Then when I distribute by -1, you're just distributing a -1 instead of dividing by -1. So that gives us -3 over x plus 4. And that's our answer for y. Now, I don't want to leave you in the lurch about this thing. I want to tell you something magnificent about dividing by -1. It's the exact same as multiplying by -1. It's literally the same, because watch here, folks. You have 3 over x divided by -1. That's the same as 3 over x divided by -1. That's -1 over 1. And how do you divide by a fraction? You multiply by the reciprocal, which is -1 over 1, because the negative sign can go on top and bottom. So dividing by -1 is the exact same thing as multiplying by -1. That's a little mind-blowing, but it's true. So had I just looked at this and said multiply by -1, that would have been -3 over x. And then take -4 and multiply by -1, that's also possible. Okay, so write down your final answer as function notation. Your inverse is, I'm going to write down 4 minus 3 over x, instead of writing -3 over x plus 4. Just because I think it looks a little nicer. Does anyone think the inverse is going to work? 4 minus 3 over x. Look at that nice pretty picture. Does it look like a little butterfly? That looks like something. All right. What questions do you want to ask about that particular process? The tricky thing was the variable in the denominator. How did we get the variable out of the denominator? We multiplied by the denominator. And then we followed classic algebra. Yeah, the -1 trick. In fact, instead of dividing out the -1, you can multiply out the -1. That's a nice trick. Now, these next two are a little more involved. The function 2x minus 1 over 3x plus 4, so I'm going to go ahead and write y equals 3x minus 1 3x plus 4. And then wait now. Do what? We do know what to do about the denominator. But first, remember, we have to switch the x and the y. There's 2 x's. So the verbiage that we should have been using all along was anywhere you see a y, put an x. And anywhere you see an x, put a y. So now this becomes x equals 2y minus 1 over 3y plus 4. We still switched the x's and the y's. But that's not very accurate to say switch the x's and the y. Because it's 2 x's and only 1 y. But you're replacing y with x and replacing x with y. Okay, so we have a denominator. We want to get rid of the denominator. And we multiply both sides times 3y plus 4. As that cancels out the denominator, it's gone. And now we have x times 3y plus 4 equals 2y plus 4. Now, I don't know of a faster, snappier way to solve this other than what we're about to do. And Lee, you correct me if you know another way. And what it reminds me of is that old classic Eastern phrase, the only way out is through. You ever heard that phrase? The only way out is through? Sometimes there are no shortcuts, you just gotta go through it. Okay, so what do? Anytime there's a variable that you want to solve, and there's more than one instance of it, you have to bring all those variables to the left-hand side and everything else to the right-hand side. So we need to bring all of our y's to the left, and anything that's not a y, send it to the right. So what do we have to do first? Yeah, we can't divide off the x because then x would be in the denominator. We don't want any denominators at all. So yeah, instead we distribute the x, and now we have 3xy plus 4x. Oh my gosh, I just had a brilliant idea. What if I just let that play while we do the rest of the problem? Like, that'd be hardcore math. Other than the fact that it's the 80s, but whatever. Wait, is it the 80s, 90s?
Hey, it was a good era.
What?
That was a great
It was a
era.
good era. Okay, so now we have all these terms. Again, we need our y terms to the left, non-y terms to the right. So I'm going to bring my 2y over to the left. You can do this in any order you like. I just have to bring my 3x minus 2y, 4x first. And then I need to send my 4x over to the right. It's a non-y term, so I move the 4x over to the right. And now I have 3xy minus 2y equals -1 minus 4x. Now see, sometimes in the middle of an algebraic process, you get dizzy and lightheaded, and you want to sit down. But you're already sitting down. But you might forget what you're doing and where you're going. What are we trying to do again? We're trying to get y by itself. Exactly right. Now there's still two y's. You anti-distribute the y out of that expression so that there's just a single y. Now we just have a single y. It's over there on the left-hand side. It's being multiplied by 3x minus 2. We divide off the 3x minus 2. And there's our answer. Y equals -1 minus 4x over 3x minus 2. Now, of course, we still want to write that in technical form of F inverse. So we say F inverse is -1 minus 4x over 3x minus 2. Now, this is the problem that I think you should practice over and over again. Not because I'm literally telling you that this problem will be on the final. But a problem like it is going to be on the final. So I'm telling you right now, practice, practice, practice. Keep doing problems like these until you can do it with one arm behind your back and your eyes closed, or just one arm behind your back. So what was the flow? We have to multiply out the denominator, distribute the x, gather our y terms to the left, non-y terms to the right, and to distribute the y, and then you're done. Right? It's a long process. This is a really good algebraic problem. This would really set you apart from people who don't know algebra if you can get your way through this problem. So practice. And number 10 is just like it. Now, first of all, before we take a break, did we do it? Yeah, let's find out. Our original was 2x minus 1 divided by 3x plus 4. There's our original. And now our answer is -1 minus 4x divided by 3x minus 2. And I hope that now your eyeballs are getting used to the symmetry around a diagonal line, that now just at a glance, you just look up there, you're like, yep, that's symmetric. You know what I'd like to do, just to put closure on this? There's only one more problem. I'd like to do it before we take a break. That way after break, we're on a different subject. So let's go ahead and try the last problem. It's going to follow the same steps. So I'm going to draw it side by side. And that way we can see it. So it's f of x equals -3x minus 2 over x plus 3. So I'm going to start by writing this y equals -3x minus 2 over x plus 3. And what do we do? Switch the x and the y. So x has become y, and y has become x's. Then what?
Multiply the denominator.
We're going to get rid of that denominator. That's goal number 1, is get rid of that denominator. We can't have variables in the denominator. So now that gives us x times y plus 3 equals -3y minus 2.
And then distribute it.
So we have xy plus 3x equals -3y minus 2.
And then you move the y and then -2, right?
Move the y terms to the left.
Yeah.
Speak more generally. Move the y terms to the left, the non-y terms to the right.
Yes.
Say it, Emily.
Move the y terms to the left and
Non-y terms.
then y.
Yeah, very good. Okay, so I'll do that. So I'm going to move my 3y over to the right, or sorry, to the left. So I have xy plus 3y plus 3x equals -2. And then my non-y term is 3x, so I subtract that over to the left-hand side. And now I have xy plus 3y Anti-distributive factor, the y.
And you divide the x plus 3
You're good, Emily. Thanks for volunteering to do that whole problem. And there we have it. I'm serious. That was great. So our inverse, theoretically, right? Is how many mistakes could we have just made? Only all of them. Right? We could have made a lot of mistakes. In theory, that composing the original and seeing if it equals x. There's one of them. And then the other one is -2 minus 3x by what the heck? Oh my gosh, that's a hoot. No way. Yes way. Where's the other graph? Watch carefully now, everybody. There's the original function. There's the inverse function. It is its own inverse. That's super crazy. It is its own inverse. Yeah, now, in fact, we can clean up the final answer so it's a little more obvious. In the original problem, what's the denominator? What's the original numerator? Yeah, I mean, it's just the same thing, but switch. So how is that? The function is its own inverse. That means that whatever you plug in, it's wild. Check it out, this is so fun. -3x minus 2 over x plus 3. If it's its own inverse, let's say you start by plugging, I'm just going to choose some random number, okay? What number should you choose? Anybody, choose any number you like. 7, sure, why not? So I'm going to plug it in, so that's -3 times 7 minus 2 all over 7 plus 3, which is -21 minus 2 is -23 over 10, which is -2.3. So I inputted 7 and I outputted -2.3. Now, if it's its own inverse, what would happen if I plug in -2.3? Should equal 7. Now, who thinks that's really going to happen? I mean, what are the odds that a function is its own inverse? That's wild. Okay, so let's try it. Then I do -3 times -2.3 minus 2 all over -2.3 plus 3. So then what is that? That's a negative times a negative is positive 6.9 minus 2 all over -2.3 plus 3 is 0.7. So then that would be 4.9 divided by 0.7, which is 7. Now, isn't that cool? That was really surprising. A function that is its own inverse. Now, big question. Is this the only function in the universe that is its own inverse? Yeah, I mean, it'd be a really interesting challenge to go try to find another one. Go find another function that is its own inverse. That's super crazy. I'm all excited about the idea. I want to stop and go home and just come up with a formula for functions that are their own inverses. Wow, I really am blown away right now. That is super fun. Okay, well, in any case, we did it. We confirmed it graphically. We did a test value. It worked.
Did you do this one in your earlier class?
I didn't. We must have skipped it. We must have just figured, hey, it's just like the other one. So you're good. And I mean, it is like the other one. The algebraic process was the same. It's just the result was so much cooler. Yeah, wow. I want to come up with another function that's its own inverse. What? All right. We will go ahead and take a break now. At the end of class, just so you know, I will pass back your test and all the notes that you gave me. So yeah, right now, let's just take a break. Time is 1:40. We'll be back at 1:50.
But I want to finish those two problems. ¿Quieres ver cómo pintar mi cuñada? Oh my god, I love that. Le hice pelo y le hice. Vamos a parar mais não. Vamos ver. Oh god. I like doing other people's makeup. But when it comes to my eye, I can't do it. I'm like, what do you mean? Yeah, like my eyes are too small to film it. They're super small. Like they're not like I don't know what else, but like you do. Like you have to. But they will. This is just like last night. I can't believe. I don't know. I don't even know. I guess just because when I was in high school, I used to have my makeup a lot, but that's about it. Stop. I should have. She does not look like. Let me show you how she looks like. I actually have her when she was. It's gonna look like makeup. Just more like more natural. And plus, just her parents are related. Oh, she's so big. Yeah. Oh, creo que sí. It's her. It's ella. Oh, okay. Ella, se me pone que llorar mi teléfono. Es la más. That's what oye, sí quiero decir que ese día terminamos más tarde. Right? I was like, Ojalá se te enfermo, yo quiero verte como perro laseado. Yo quiero verte como perro. Bueno, awesome. Oh, no, this was in high school. I don't know. Oh, sure. This one I did my sister's makeup. Yeah, it's chinita. She's so pretty. I'm like jealous of her. She's tall. I'm like, I need to. She's already 15 too. Oh wow. Yeah. Sister, look at her long picture. She's that chinita. Mama bear. She's so cool. I want you to meet her. That's so neat. My mom is like, she's like my best friend. I feel like we're closer than ever. I feel like the older we get. Mira, ella es ella de Gris. Oh, she, I mean, honestly, everybody changes themselves. That's so beautiful. I mean, I think
Is Greek grandma's in here?
Oh, sure.
Okay. Yeah, I wish I had curly hair. My mom has curly. And I was like, so yesterday, bro, serious? It was cute. And I guess she says she's older. I was a student council. Después los fines okay, I have to find this say. Yeah, a couple months ago, me tuve que poner por pijama. I'm like, ya me dices. No, she I'm not playing one time. She turned, had just turned 50, and then my mom was like, le tomó como 20 años. It's my mom, my sister. No, my sister ate it. My brother. It's my stepbrother. And Martin. ¿Por qué te ríes? Te cayó. Es frío. Ay, invece. Mira, look. Ay, and I used to complain that I was like, no. Y el vecino me queda. Ay, pon las pilas. El verano ya viene. Mi mamá que ya, a ver cuánto. Es que hay un cero motivación en la casa. Que no. Hoy tengo un parque frente a mi casa. No sé, es que, okay, the area where I live is like, I'm trying to, I don't like going outside. Yesterday, all 51st and common, 51st and in school was closed because there was a lot of like drugs, racing. No, it's not a lot. It's just a bunch of cars. Never being picked up. Pues que lo traía las playas, no lo tengo. No, nomás hablaste, pero para lo traerlas como like, oh, hablaste, pero bueno, así es de ojito. Aquí, no, aquí es muy difícil. Oh, de lado. Yo sí lo.
Right. So, we get to try something a little different now, and we're going to solve some functions with radicals. And after we do these, I think we should have a little time left over, and we can look at some of the homework from the Moore website. Now, recall, what are we trying to do anytime we solve an equation? What are two ways to say what you're trying to do when you solve an equation? You're correct. You're isolating the variable. Very good. That's okay. So there's three ways to say what we're saying. One is you can say you're isolating the variable, and when you isolate it, what should be on the other side? Like if you've isolated the variable, then you're going to have x on one side and what's on the other? Yeah, some number, right? Maybe you'll have multiple solutions, but there should be a number. And what is that number? It's a coordinate. It's a very special coordinate. It's on the x-axis because the solution is the solution to an equation is always an x-intercept. That number right there is always the x-intercept, right? Because when you have some sort of function, the solution, the x-intercept is always some function equals 0. So when you solve an equation, you believe it or not, anytime you solve an equation, like look at that first one, x plus 1 equals 3x plus 7. That doesn't look like an equation equals to 0. But I can very easily just move that root over to the left, and then it's x plus 1 minus root 3x plus 7. And that's equals 0. So I have a function equal to 0, so solving this equation is the same as solving that equation, which means graphing it and finding the x-intercepts. So the solution to any equation is always an x-intercept. And finally, what does that number do? If you take the number and you plug it back in, what will happen?
Or I cancel that.
What happens if I find the actual solution and I plug it in here and I plug it in here? It should
Equal to 0.
it should be equal to itself. It should be true.
Okay.
right? Once you simplify that out, it'll be like 10 equals 10. Which, to be fair, if you subtract 10 from both sides, that'll be 0 equals 0. So yes, anytime you find the correct solution, you should be able to plug it in and simplify the whole thing down to 0 equals 0. Which is kind of ironic that anytime you find a solution, if you plug it in, it'll make the equation 0 equals 0. Sounds so vacuously unimportant. 0 equals 0. Okay, so that's what we're saying. We're isolating the variable, we're finding the x-intercepts, we're finding a number that you can plug in to make the equation true. So look at that first equation right there. X plus 1 equals the square root. We're looking at all of these equations have some sort of a root in it. How many x-intercepts will a root have? Here's the simplest square root function. How many x-intercepts does it have? 1. Now let's look at the one that we're looking at. X plus 1 minus the square root of 3x plus 7. How many x-intercepts does it have? Yeah. Now, Gabe, I can tell you're tempted to say 2, but that was in polynomials. With polynomials, the highest exponent on x tells you the most number of x-intercepts you'll have. With a square root graph, the most number of x-intercepts you'll have is 1. Always 1. Because a square root, typically when you look at the graph, it just starts heading up in a very continuous way. It doesn't double down back on itself like x-intercept. Everybody, you just kind of know that heading in. This thing will have 1 x-intercept. It'll have 1 x-intercept. This also will have 1 x-intercept. This will have 1 x-intercept. So anytime you have a radical equation, and the other terms are just x, not a power of x. Like the highest power on x, there's just 1. So there's just 1 x-intercept that we're looking for. So everybody, you can go ahead and take a look. Here's the first graph. What's our solution? 3. Yeah, 3. Apparently, if I plug in the number 3, it'll make that equation true. Let's try it. Everybody, just for fun, let's go ahead and try that first solution. Number 9, we're claiming, because we just looked at the graph, that if you take x plus 1 equals root of 3x plus 7, and you plug in 3, apparently it'll be true. So 3 plus 1 is 4, 9 plus 7 is 16, and is 4 equal to 4? Yeah. And again, if you subtract 4 from both sides, you get 0 equals 0. So that's really technically how every algebra problem ends. You find the number that you plug in to make it true, and if it is true, you can subtract the number from both sides and you get 0 equals 0. Okay, so we're just kind of talking about what this problem means. And our goal is to solve it algebraically. I just solved it graphically by looking at the graph and seeing where the x-intercept was. But now let's go ahead and solve it algebraically. So we have this equation, x plus 1 equals the square root of 3x plus 7. Now, I'd like you all to know and keep in mind that algebra is motivated by inconvenience. All right, so like what's inconvenient about this equation? What's kind of the headache? Well, okay, that's true, x is on both sides. That's inconvenient. What's the bigger inconvenience? Yeah, the radical symbol, right? So algebra is motivated by inconvenience. Whatever you find to be the most inconvenient, try to get rid of it. Just like we did a second ago with all of our problems with a denominator. We had some problem, what was the problem that we just did? We had this problem where x equaled 4 over 3 minus x, something like that? No, 3 minus y. Yeah, there we go. What was the big inconvenience here? Yeah, the fact that there's a denominator, right? So algebra is motivated by inconvenience. Find whatever's most inconvenient to you and try to fix that. So here the inconvenience was the denominator, so we multiplied both sides by the denominator to cancel the denominator, and bam, no more denominator. Right now, we're being inconvenienced by the square root symbol, so we'd like to cancel the square root symbol. How do we cancel things? Using inverse operations. So if we're inconvenienced by a square root symbol, how could we cancel it out? By squaring it. The essence of algebra is to cancel things, to destroy things. So I'd like to cancel out and destroy the square root symbol. So how do we do it? We just square both sides. Now, something interesting just happened by squaring both sides. First, we achieved our goal, and we canceled out the inconvenience. There is no longer a square root symbol in the problem. That's really nice. On the other hand, we just squared x plus 1, and so now I'm going to go to FOIL it. We FOIL out x plus 1. That's gonna be first, x squared, outer, 1x, inner, 1x, last, 1. Which then becomes x squared plus 2x plus 1 equals 3x plus 7. We took an equation that had one x-intercept with one inconvenience, a square root, squared both sides, got rid of the inconvenience, but now how many solutions, how many x-intercepts does this equation have? 2. So that's kind of interesting. Philosophically, we went from an equation that had one x-intercept, and that was the one we're interested in. But now all of a sudden we have a graph of 2 x-intercepts. So that means one of those x-intercepts is the one we're interested in still, but the other x-intercept we're not interested in. It's not imaginary, it'll be extraneous. Yeah, it'll be a number. The one we're interested in, we'll still be able to plug it back in and make a true sentence. But the other one that we just created by squaring this will be a number that if we plug it in, it won't make it true.
That freedom.
What? Oh, what's it?
Oh, I said therefore you won't use it.
Yeah, therefore we won't use it. Okay, so now keep in mind, we're in the middle of a long algebraic process here. What do we want to do next? We want to solve for x. Yes, always. Bring all the terms over to one side. That's a good idea for a couple reasons. One, by bringing everything to one side, you can graph it on Desmos. But also by bringing everything over, now watch what I'm about to do, folks. I'm about to do something very sacrilegious. I'm going to move the 3x over and the 7 over. That's a no-no in algebra, right? I mean, at least that's my understanding, that you're never supposed to do 2 action steps at once. You're supposed to move the 3x over and then move the 7 over. But I just can't help myself. It's just 2 terms. We want to move them over. So I did it. If you tell on me, I understand. Okay, so we have all of our terms over to the left. And now we want to solve this. Now keep in mind, this is why we set it equal to 0. Because what are we about to do with this thing? You could do the quadratic formula A, B, and C, and you could do the quadratic formula. Or what multiplies to make 6 that adds to make 1? Yeah, we can go ahead and do a factor table for -6. So that's 1 and 6, 2 and 3. We're multiplying to make a negative, so it's a plus times a minus. So one of them is plus, one of them is minus, and they have to add up to -1. And that'd be the plus 2 and the minus 3. So now we just factored it into x plus 2, x minus 3 equals 0. And because we had it all set equal to 0, we can now use the 0 product rule and say this times this equals 0, and therefore x equals -2, and x equals 3. Now, first of all, who remembers where the x-intercept actually was? 3. Yeah, it was at 3. Take a look again. Here's our graph. The x-intercept was at 3. And yet, somehow, this graph has now produced a second x-intercept. Let's look at that graph real quick. The equation we got to was x squared minus 1x minus 6. What do you notice about the parabola and the original square root function?
3, 2, x-intercepts.
Yeah. The parabola has 2 x-intercepts, -2 and 3. Aren't those the ones we just found? -2 and 3? But where do they overlap?
Or the 3.
Yeah, the 3. So the 3 is still the solution we're interested in. It just so happens that there's an additional root or additional x-intercept the parabola has that is not shared by the square root function. So how do we know, just by doing the algebra, which one of those works, the 3 or the -2? Exactly right, we have to plug it back in. That's always the end of every algebra problem. Doing algebra and isolating the variable, so like that first idea, isolating the variable, yeah, we just isolated the variables. But that's never the end. Now what we do is we take the -2 and the 3 and we actually plug it in and see if it works. Does it make a true sentence? So we're going to take the original problem, x plus 1 equals the square root of 3x plus 7, and plug in -2. Then we'll plug in 3, and we'll see what happens. Now, before we do that, I need to make one thing clear about this square root symbol right here. That square root symbol, what's the sign in front of it? A plus. Do you all agree that there's an invisible plus sign in front? I mean, it can't be a negative sign. If it was a negative sign, they would put a negative sign. The sign in front of the square root is a plus. Not a plus or minus. Did they put a plus or minus there? No, it's a plus. So when we plug this number in, I'm going to plug in a -2. -2 plus 1 equals the square root of 3 times -2 plus 7. -2 plus 1 is -1. And then that's the square root of 3 times -2 is -6 plus 7 is 1. And they're asking for the positive square root of 1, not the plus or minus square root of -1. just a positive one. And so we get this. Is that true? That's false. So that did not work. But it all hinges upon our understanding that when you do a square root in the original formula, they're asking for the sign that's in front of it. In this case, they were asking for the positive square root, not the plus or the minus. If it was either plus or minus, you could be like, well, I choose the negative square root because then it would be true. You don't get to choose. You take whatever sign they give you. So that's false. Now let's try the other way. X plus 1 equals the square root of 3x plus 7. And now we're going to plug in 3. So now that 6 equals the square root of 9 plus 7 is 6. What did I do wrong? That's not 3 plus 3. It's 3 plus 1, which is 4. There. So now I have 4 equals, and this again is the positive square root of 16 that they're looking for. 4 equals 4. That's true. So what that tells us is that the negative 2 was extraneous. This is a really nice problem because we can go back now to the beginning and talk about the 3 definitions we gave of solving an algebra problem. First of all, did we isolate the numbers? Yeah, we isolated x. X was either negative 2 or x was 3. Did we find the x-intercept? Well, yeah, for the original graph, the only x-intercept was 3. For the equation we created, there were 2 x-intercepts, negative 2 and 3. But as it turns out, that negative 2 was not an x-intercept for the square root graph, and in fact, negative 2 does not make the original equation true. It makes it false. So 3 is the only solution that makes the equation true. What do y'all feel about that? All right. Now I want you to notice this equation has one solution, but when you square it, but when you square it, there's going to be 2 x-intercepts. And this, well, we're going to have to look at that one separately because they wrote it as a fractional exponent. But the key thing to note is that anytime you have a square root equation, there's just 1 x-intercept. But in order to get rid of the square root, you have to square it, and when you square it, you generate a power of 2, which gets 2 x-intercepts. Okay. Everybody ready for the next one? Now, in number 10, we have x plus root 3x plus 10 equals negative 2. Now again, what's the inconvenience in this problem? You know, the square root. In order to cancel the square root, you need to square. But right now, if you just arbitrarily squared both sides right now, would that work? Would that cancel the root? Yeah, so does everybody see this? I want Emily and Valeria to see this too. If I just square both sides right now, is that going to cancel the root? I mean, squaring cancels roots, so you might say, well, yeah, sure, it's going to cancel the root. But everybody watch closely what happens. If I just squared right now, I would have to FOIL x times root x 3 plus 10 times x plus root 3x plus 10. That equals 4. And then when I FOIL that, first would be x squared. Outer would be x times root 3x plus 10. And then inner would be x times root 3x plus 10. And then last would be root 3x plus 10 squared. So did any of the roots get canceled?
Unless you want the x to be.
Well, hold on. First, my first question, did any of the roots get canceled? Yeah, this one did. This one got canceled. The squaring the root cancels it. So now what do we have? This is a 1x, that's a 1x, and now I have x squared plus 2x root 3x plus 10. Because I technically have 2 of those things. So I can add them together and find like terms make it 2. And then that plus 3x plus 10 equals 4. Did I cancel my root? No. And in fact, is this equation now worse than the first one? Yeah, things got worse, they didn't get better. So you can't just arbitrarily square an equation that has a root in it. We have to do something first. What do we have to do first? I hope now you wrote that down. Yeah, before you can square your root, you have to isolate the root. What made this problem unfortunate was the fact that there was an x sitting there next to it. And therefore, when you squared it, you actually had to FOIL. We don't want to FOIL. We want to just square that term all by itself. So we have to move that x over to the other side to isolate the root on one side of the equation by itself. And that's important enough to write down. Isolate the root. Because we're absolutely right that to get rid of a square root, you need to square it. But you just can't square it arbitrarily. You need that square root all by itself, sitting on one side of the equation. So that now when you do square both sides, what will happen? Now will the square root cancel out? Yeah, now the square root will cancel out completely. So that cancels out, and you have 3x plus 10. And on the other side, you have negative 2 minus x squared. So anytime you have a square root equation, you need to first isolate the square root. Then you could square both sides. And of course, by squaring both sides, you are always going to end up having to FOIL that out. So now we have negative 2 minus x times negative 2 minus x. Which at first glance, you might think, oh man, all these negatives are going to FOIL all that out. But every time you multiply any two of these numbers, it's going to be a negative times a negative, which is positive. So it's actually not that bad. So now first is 4, outer is 2x, inner is 2x, last is x squared. And we now have 3x plus 10 equals 4 plus 4x plus x squared. So a couple of things. We just did a whole lot of work. We got rid of the square root symbol, which is wonderful. But we now generated a quadratic, which has how many x-intercepts? 2. So it's kind of like we traded off one evil for another. We had a square root symbol that we wanted to get rid of, and the trade-off was creating a new function that has 2 x-intercepts instead of 1. And we'll have to check both of those x-intercepts to see which one is extraneous or which one actually works. Okay, so now, again, we need all of our terms to one side. Since x squared is already on the right, I'm going to move all my terms to the right. So I'm going to move my 3x over. I'm going to move my 10 over. And so now I have x squared plus 1x minus 6. And all that equals 0. I'm going to write the 0 on the right-hand side. Again, I kind of did something sacrilegious here. I moved the 3x over and the 10 over. Lee, do you ever move two terms over at once?
Yes.
My answer is only when no one's looking. But
I always look over your shoulder first.
yeah, exactly. What do you do before you move two terms at once? You look over your shoulder. Okay, so now we have this. So again, it's a quadratic, it's parabola. It has 2 x-intercepts potentially. So we have to first factor that. And how does it factor? What multiplies to make negative 6 that adds to make 1? Yeah, 3 and 2 again, where one of them is negative and one of them is positive. So it's the plus 3 and the minus 2. So we have x plus 3, x minus 2. And therefore our solutions are x equals negative 3 or x equals 2. Now in the previous problem, the negative solution didn't work. Do you think that we can generalize and say, hey, just going forward, the negative solutions won't work? No, that'd be a big ass assumption. That'd be a big ass mistake. I was trying to make a word play there. That just sounds.
It didn't work out.
It didn't work out. Assumption. Okay. So we need to check both of those to see which one works. So we're going to take the original equation, which is x plus root 3x plus 10 equals negative 2. Let's see which one works. So I'm going to try the negative 3 first. Negative 3 plus root 3 times negative 3 plus 10 equals negative 2. Now, I just want to say this real quick. This is right about where I lose a lot of students. I'm like, well, do I have to do that? And the answer is yes! This is the rest of the problem. This is the rest of the problem. That'd be like if you went over to your friend's house to help them move, and you took everything off of the U-Haul, and you just set it in their front yard. There, I helped you unload the truck. I'm like, I didn't ask you to help unload the truck. I wanted you to move it into my house. Like, finish the job. Okay, so yeah, we're plugging it in and we're checking to see if it's a true statement. So negative 3 plus negative 9 plus 10 is 1. And that's negative 3. Again, this square root is just positive, so it's plus 1. And does negative 2 equal negative 2? Yeah. So that was true. So far, negative 3 is correct. Now that doesn't mean that we can just forget the 2, scratch it out, and just assume that it's extraneous. We need to actually check, because we could have made a mistake somewhere. So now we'll plug in again, x plus 3x plus 10 equals -2. This time I'll plug in the 2. 2 plus root 3 times 2 plus 10 equals -2. So that's 2 plus root 16. Now we can probably stop here, because well, a positive plus a positive equal -2. So that thing's false, and therefore x equals 2 is extraneous. So let's see here. Let's graph it, see how it looked. The actual graph moving everything to the left, x plus the square root of 3x plus 10 plus 2. So there's our actual graph, and there is only one x-intercept, and it's at -3, just like we expected. But when we transformed that equation into a quadratic, getting x squared plus 1x minus 6, we did in fact create a quadratic, and it did share the x-intercept at -3, but the parabola had this extra x-intercept, which was not valid.
For the first one you graphed, you just did because it was equal to -2, you just moved it over.
Yep.
So it'd be positive 2.
Exactly. Well, I moved it over so that it would be equal to 0. Yeah. So everybody, just remember, you're allowed to take any graph or any equation, and if you just move all the terms to the left so that it equals 0, you can graph it, and the x-intercepts will be the solution. And yeah, so that's -3. Okay. Did we? Yeah, we took a break, and it's 2. Okay. Yeah, we still have time. I lost track of where we were. So we have 2 more questions, and then we can do homework, or look at some questions from homework. So, what more questions would you like to ask right now first?
Can we go one by ourselves?
Yeah, absolutely. Yeah, here's what I'd like you to do by yourself. None of the other ones are like this, Emily. But you can certainly go home and just try those again. Don't look and try it again. I'm so sorry that there's not another one, Emily.
Oh, it's fine.
Okay. So, number 11 says x to the 3/2 equals 8. Now that doesn't look like a square root problem. Yes, but it is. And one way you can think of this as a square root problem is you can separate the 3/2, and you can see that that's really 3 times 1/2. And if you recall your rules about exponents, let me write them down so you can all see them. Everyone, do you recall that x to the a times x to the b is really x to the a plus b? And then x to the a divided by x to the b is x to the a minus b. And x to the a raised to the power of b is actually x to the a times b. Okay, so those are some exponent rules from your past. And so we could rewrite 3/2 as a whole number times a fraction. And then do you also recall that something to the 1/2 is actually a square root? So what we have here then is the square root of x cubed. And that's it. It's just a matter of rewriting the fractional exponent as a whole number times the fraction, and that way that unit fraction becomes a root. Because now technically we could go ahead and do this with normal algebra. There is no, it's not like the previous 2 problems. So x is being cubed and then square rooted. So we'd square both sides. That would cancel out the square root. So now we have x cubed equals 64. And now this you can type into your calculator or you could think about it. But what's the opposite of cubic?
Square.
Cube rooted. And so now we have x equals the cube root of 64. Now, your calculator does have a cube root button. So you can just use the cube root button. It's in the math option. If you go into your calculator and hit my favorite button, math, there should be a button that says solve.
Right.
That was more abstract. Okay, so if you hit math and then down it a little bit, there's a cube root button, so you can hit cube root of 64 and it'll tell you the answers for. Or everybody remember that when you do a root, it's really 64 to the power of 1/3. So when you do a root, it's the same as raising it to that power, which is actually what we just used a second ago. That if it's the square root, it's really x to the power of 1/2. If it's the third root, it's really x to the 1/3. If it's the fourth root, it's really x to the 1/4. So you can also type that in your calculator, 64 caret parenthesis 1 divided by 3 parenthesis. Try that as well, make sure you get the same answer. 64 caret parenthesis 1 divided by 3 parenthesis.
Are they allowed to take it another way as well?
What?
Are they allowed to take it another way as well?
Yeah, what?
I was thinking, because we have 3 halves in the power, right?
Mhm.
What if we take everything to the power of 2/3?
Right. Absolutely. That's another solution we can do. Yeah, the reciprocal. So folks, let's do that as well. We know that if you raise a power to a power, you multiply the powers. And taking a look at this one again, you have x to the 3/2 equals 8. And what we want to do is get ourselves to x equals a number, right? And x is the same as x to the 1 equals a number. So how can I manipulate this expression so that it becomes x to the 1? You raise it to the power of 2/3, which is the reciprocal. Because that way now, 3/2 times 2/3 is 1. And 8 to the 2/3 you can type directly into your calculator as x caret 2 divided by 3. So try that as well. Try 8 caret 2 divided by 3.
Can you do both last or you want to?
You can do it any way you like.
I know it's kind of a cheap shot, that's why I was asking.
Yeah.
No, it's not a cheap shot. It's a very good solution. And to be honest, this morning, all I did was that way. But I felt inspired to share this to kind of review
Those,
some more old rules.
most definitely.
Hmm?
Most definitely.
All right. We have one more problem here, and I'll go ahead and tell you that this is one that we can simply solve graphically. I think it's a lovely solution graphically. Remember that we've previously talked about solving quadratics and, well, basically parabolas with inequalities. And we came up with a couple rules, or verbiages anyway. And we said, when we say we want f of x less than or equal to 0, what are we saying about the graph? Let's say it's a parabola. When we say we want f of x to be less than or equal to 0, what part of the parabola are we interested in? If we said f of x was equal to 0, we'd be interested in the x-intercepts. Well, what if I say f of x is less than or equal to 0? What are we interested in? What part of the parabola?
The negative side?
The negative side, which means below. All right, everybody remember that? Less than or equal to meant below. Now, Valeria, a couple problems ago, we saw x less than or equal to -4. That's x being less than, so that's left or right. When it's f of x, that represents up or down. Okay, so that was f of x less than or equal to 0. And then what if we ask for f of x greater than or equal to 0? What are we interested in above? Yeah, where is it above? So do you all remember doing that? So greater than or equal to means above, less than or equal to means below. And so here's the problem. 10 minus root x minus 2 less than or equal to 11. Now, first of all, we didn't have a definition for 11. We had a definition for 0. But it works the same way. This means when is this graph less than 11 units tall? Here we're saying less than 0 units tall. So let's go ahead and just move the 11 over. So we have -1 minus root x minus 2 less than or equal to 0. And we're asking when is that function less than or equal to 0? And so you can just graph it. And you can look to see when is it below the axis. Now you can also solve this problem algebraically, but I'm just as happy that everyone learns how to interpret the problem graphically. So, take a look at this fun problem. When is it below the x-axis? Yeah, very good, always. It's always below. So what does that mean? Can we just write always? Keep in mind we're asking what x values can I plug in such that it'll be below?
So it'd be
If I plug in the x value 2, will it be below the axis?
Yeah.
If I plug in the x value 4, will it be below? If I plug in 6, will it be below? What if I plug in 1? Will the graph be below the axis? Yeah, I mean, you could say negative infinity to be funny, but the graph doesn't even exist. So if I plug in 1, is the graph below the axis? No, because the graph doesn't even exist. So what x values can I plug in to make it below the x-axis? From 2 to infinity. Wait, I'm sorry, Omar, is that what you said? From 2 to infinity? That's correct. I thought you were saying over here that it was at negative infinity. I'm sorry, I misheard. Yeah, so what we're saying here is that when is this, okay, this guy, below, well, the graph is that. It starts at 2. So on a number line, when we talk about domain, it would be everywhere from 2 to infinity, which means our domain is 2. That means any number you choose between 2 and infinity, the graph will be below the x-axis. This is a really interesting solution because there's no algebra involved. We didn't do any algebra. We didn't tell the story of x. We didn't solve. We just thought about what it meant graphically in terms of the graph. And then we had to think about domain as well. All right. Well, that's it for section 5.2. So let's take a look at some homework. Let's look at 5.1 first. Now, what I would do if I were you is take out a sheet of lined paper so you can write down some solutions. That way you'll have these as notes when you go home. Look at these new erasers, work really well.
Nice.
I'm
Yeah.
impressed.
Right.
Apparently, all you need is a new eraser. And then it actually works.
Any idea how old the old racers were beforehand?
Oh.
Probably not, right? I still go with my.
All right, so folks, in the previous class, people asked questions about domain problems, and I'm happy to do the domain problems. But I'm just curious if any of you have any questions you'd like to ask. I mean, in theory, if you have questions, you've already emailed them to me, right? But if you have a question right now you want to go over, let's start with that. Any questions from 5.1?
Yes.
What? Which one?
Oh, I need to look. 'Cause
Okay.
I put up another one.
Well, I'm going to scan through real quick and look for the domain ones. Because the first few are all just compositions.
Oh, yeah, that one.
Okay, there we go. So 6. We'll do 6. We'll do 6, 14. Yeah, we'll start with 6 and 14. All right, so in number 6, everybody you can write down on your paper, 5.1, number 6. Because when you get home, you'll get a problem for number 6, looks just like this one. And it says, let f be root 2 minus x. And then let g be x squared minus 2. No, x squared minus x, right? And they want the domain of f of g. So we can go ahead and find f of g. So f circle g, the function, is really f of g of x. So that means you start by writing the structure of f, which is the big square root of 2 minus something. And then you plug g into it, which is x squared minus x. So far, the only part of the skill from this chapter of doing the composition, we're done. That's the composition. You could distribute it. So that it would be 2 minus x squared plus x. And you can put the terms in order. Negative x squared plus x plus 2. But still, that's the composition. So the composition function is that. So we want to remind ourselves, how do we find domain? Remember, domain is every number in the universe that you can plug into the function, except for an input that would cause you to divide by 0 or square root a negative. So those are the only two things you can't do, is divide by 0 or square root a negative. Now looking at our function, is there a denominator? Well, there's no denominator, so we're in no danger of dividing by 0. Is there a square root? Yes. So we don't want to square root a negative. So remember what that means. Whatever your radicand is inside. Whatever it is, we don't want it to be negative. And the only way to really say that, if you don't want the radicand to be negative, that means, like look at an underline, here's 0, here's positives, here's negative. I don't want it to be negative, so what's left? Yeah, so that means we set the radicand greater than or equal to 0. So that's how you do the domain test. You take whatever's underneath the square root, and you set it greater than or equal to 0. So let's do it. We're going to take whatever's under the square root and say negative x squared plus x plus 2. I want that to be greater than or equal to 0. Now notice, we now have a problem that we can solve by interpreting this graphically. So graphically, you could just go ahead and do it. You could just graph that and see when it's above the axis. So let me show you that. So graphically, we're doing the problem negative x squared plus x plus 2. Is that it? So when is it above? Isn't that what it's asking? Yeah. When is it above? Between negative 1 and 2. So the function is above the axis between negative 1 and 2. So already that's the answer. So on a number line, here's our domain number line. We go between negative 1 and 2, and it's greater than or equal to. So it's between negative 1 and 2. And that's our domain from negative 1 to 2. Now keep in mind, you could also have solved this actually by factoring. So if I multiply all the way through by negative 1, just so that I don't have a negative x squared. So now that's x squared minus x minus 2. And because I multiplied by a negative, I flip the symbol. Now I can factor this. What multiplies to make negative 2? 1 and 2. It has to add to negative. So that'd be a negative 2 and positive 1. So that's x plus 1, x minus 2. And therefore my x-intercepts are negative 1 and 2, which are exactly what we just knew. So that means I would have a parabola whose x-intercepts are negative 1 and 2, and my original parabola was upside down. And therefore, when is the parabola above the x-axis? Between negative 1 and 2. So we get the same answer either way. That's a couple different ways to think about it. As always, we might wonder, are we right? So we go into more, and we're going from negative 1 to 2. And that's it. Questions about that one? Now, to be fair, folks, that's a lengthy problem, isn't it? And that problem actually draws upon all the knowledge that we've had for this whole semester. The composition was teeny. The step of doing the composition was just the very first line of work. Then we had to think about it as a parabola. We had to know how to do a domain test of saying the radicand had better be greater than or equal to 0. And then we either had to graph it and look for when the graph was above the axis, or we had to factor it, find the x-intercepts, make a graph ourselves, and still think when is it above the axis. So that was actually a very sophisticated problem. That's like the equivalent of a 5-paragraph essay as opposed to a short paragraph response.
Okay, here's one more good one. Oh yeah, we have time. Now let's take a look at each of these before we actually do the problem. So there's the problem. Well, let's look at those two functions. H of x is 1 over root x. And p of x was x squared minus 4. So again, you can label this. This is assignment 5.1, number 14. So let's do the domain of each of them independently. So in this one, are we going to potentially divide by 0? Yeah. So remember what you do. If you have a denominator, you circle the entire denominator and you say, hey, I sure hope that denominator is not equal to 0. Right? That's the first test you do. You take the whole denominator and say, I don't want the denominator to equal 0. And then you solve. So we're going to square both sides. And now we know I don't want x to equal 0. So that's the first part of our domain. We know that x can't equal 0. But then notice, we also have a square root. And we don't want to square root a negative. And so what do? You circle the radicand and you say, I want my radicand to be greater than or equal to 0. Okay, so that's the second part of my domain. What I've found out now is that for this function, I want x to be bigger than or equal to 0. But I don't actually want it to equal 0. So that means that my domain for the function h of x is from 0 to infinity. So what does that tell us? What kind of number can I plug into h of x? Yeah, any positive number. So long as it's a positive number, I can plug it in and I'll be fine. Now what about p of x? Do I have a denominator? No. Do I have a square root? No. So the domain is all real numbers. I can plug any number into this that I like. The domain is negative infinity. So there. We haven't even done the problem yet. Well, we haven't done the problem yet, but we've practiced again domain questions. All right. So folks, again, here's a handy dandy nice way of doing it. Whenever you have domain problems, you need to look for a denominator with an x in it, in which case you say denominator not equal to 0. Or you're looking for a square root with a variable in it, in which case you do radicand is greater than or equal to 0. So if you want, like, put something in your notes that you can memorize, those are your only two domain tests. You set the denominator not equal to 0, solve with algebra. You take the radicand, greater than or equal to 0, solve with algebra. Oh wow, Valeria, you can write right on your tablet?
Yeah.
Well, that's nice.
That's awesome.
Okay, so let's try the first problem. It says, find the domain of h of x divided by p of x. So h of x is 1 over root x, and p of x is x squared minus 4. So, do we have a denominator? How many denominators? Yeah, we actually have that denominator, and we have this denominator. So there's actually two. We'll say we don't want that denominator to equal 0, and also we sure don't want that denominator to equal 0. That's a denominator of this fraction, and this is a denominator of the whole fraction. So you do the denominator test for both of them. And then, do we have any square roots?
Or, yeah, on the top.
There, I'm going to write it as the rule. I'm using the verbiage as the rule under which I'm doing my work. Yeah, I've got that square root. So my radicand, I want there. So I have 3 different pieces of information feeding into my domain. We solve all 3 of them separately and make a number line and show the result. Here, we just square both sides, and we find out that x better not equal 0. Here, we move the 4 over and find out x squared better not equal 4, square root both sides, x better not equal plus 2 or minus 2.
And then here, we just know that x has to be bigger than 0 or greater than equal to 0. So you take all three of those pieces of information and you layer it onto one number line. And you say, well, I don't want x to equal 0. I don't want x to equal 2 or negative 2. So I'm just putting in open circles right now to show that I'm not allowing those numbers in my domain. And then finally, I know x has to be bigger than or equal to 0. So that means I'm just going to shade to the right of 0. I want to show you another way of thinking about that. Let's say I had started over here, and I said, hey, x just has to be bigger than or equal to 0. I would have started like this. And then what would I have done? I would have gone back and deleted certain numbers. I would have deleted the 2. This negative 2 doesn't matter. It wasn't over there. And then here I would have deleted the 0. So either way, you end up with the same answer. So what's my domain? Using interval notation between 0 and 2, from 2 to infinity. So let's try that out and see if it worked. The domain of that fraction is 0 to 2 union 2 to infinity. And it works. Is that okay?
Yeah.
Okay. All right, so let's try the next one, folks. H of P of X. We need to write down the formula first. So we do the structure of H, which is 1 over root something. And then we input the function of P, which is x squared minus 4. Now again, in terms of structuring your work, I'm suddenly really liking this idea of setting it up with the words. So I have my denominator test. My denominator better not be equal to 0. And I have my radicand test. My radicand better be greater than or equal to 0. So do I have a denominator? Yeah, the whole darn thing, the whole denominator, I'm saying it better not be equal to 0. So I go ahead and solve that. Square both sides. X squared minus 4 better not equal 0. Add 4 to both sides. X squared better not equal 4. Square root of both sides. X better not equal positive 2 or negative 2. And then we also have a radicand test. We have a radicand here. We're saying x squared minus 4 better be greater than or equal to 0. So we're saying x squared minus 4 better be greater than or equal to 0. Now here is a problem that could be a little tricky. Because in order to solve this, here's what you can't do. X squared minus 4 greater than or equal to 0. You can't just move the 4 over and then square root both sides and say x has to be greater than or equal to plus or minus 2. Because what does that even mean? Plus 2 is over here, negative 2 is over here. We're saying x has to be greater than both of them? Like that? Because if x is greater than negative 2, you shade this way. And if x is greater than 2, you shade this way. And so we're saying, really, that all of these are solutions? Because I don't think so. I think if I chose a number here like 0, 0 squared minus 4 is 0 minus 4 is negative 4. That's not true. Negative 4 is not greater than or equal to 0. So you can't just, when you have an inequality, you actually can't square and square root both sides. You have to fall back on the idea of above the x-axis and below the x-axis. Here they're asking for above the x-axis. So we would need to graph that. X squared minus 4 is difference of squares. That's x minus 2 times x plus 2. And so those would be my x-intercepts. Negative 2, positive 2. It's a parabola facing up. And so when is it above? Yeah, those are actually our solutions. Anything to the left of negative 2 and anything to the right of positive 2. And now notice, we're also, from our other test, we're saying x had better not be 2 or negative 2 itself. So I can actually turn those into open circles. And now my domain is ready to be written down. We're looking at any number to the left of -2, all the way to -infinity, anything to the right of 2, all the way to positive infinity. And so our domain would be -infinity, -2, union, 2 to infinity. Let's see if it works. -infinity, -2, union, 2, infinity. Yep. Now, by the way, folks, you'll notice that the author of this video is about to do an entire problem just like this. So if when you get home you're ever not sure, these videos are very good because he's going through the entire problem just like it. Okay. Well, I think I better stop there and give you back your tests and your papers. So I'm going to get that for you. When you get home, please let me know if you have any other questions. Always email me with your questions. Now, who was actually here? That was not Hector. Homer was. Lydia, Emily. All right.
Wait, no?
Oh, I just happened to have them on top. I guess I just happened to have them on top. Here you go. And Omar, I never gave you back your old test. Here's your previous test. And here's your new test. And the wedding is your test. And Hector is not here. And Nadine is not here. And Gabe is yours. And Emily is yours. Okay, so folks, here, a word for all of you. Take your test, and whether you missed, however many problems you missed, your job is always, when you get your test back, to go through and learn each problem that you missed. Right? The test is not over when the test is over. The test is only over when you know how to solve every single problem. So whether you missed 1 problem or 10 problems, go back through the test and learn how to do it. You can pull up the solutions that are posted online and look at the solutions to the practice test, or you can come see me, work with me in my office. And but no matter what, take a look at your test and come back and see me if you have questions, because I want to help you know it. Because at least a handful of those questions will show up on the final exam. And so you want to know how to do them all. Okay, well, we have a couple minutes left, so, this is your time. You have questions for me? Come ask me.
You can also come to me as well.
And come see Lee as well. You can go over to the test with Lee. You can go over to the test with me. Hey, Omar. Oh, hey, wonderful. Let me put these in right now. For you.